Chapter 6 is called the normal distribution. It's a continuous distribution, unlike the discrete distribution of, for example, the binomial. But the normal distribution is also recognizable as the bell-shaped curve. Kind of a bell shape, how it curves down and then curves out at the base. It's probably the most famous distribution. We're going to use it with areas being identified with probabilities, areas underneath the curve. But first, let's look at the curve itself and kind of the way things are distributed. If my variable is the x-axis, I've got low values of the variable and high values of the variable. And the typical values, the ordinary or normal values, there are more of them. There's more area under the curve there. For extremely high values, the curve is lower. There's less area there. There's lower probability. For the extremely low values, same thing. That's a lower curve. The area down there would be smaller for a given piece of it. This is how normal things, not everything, but a lot of regular things are distributed. And one of my favorite examples is heights of fully grown people. Everybody grows to their whatever their full height is. Most people are around average height, maybe a little more, maybe a little less, maybe right at about average. But very few people are much taller than average. So people that are 7 feet, 8 feet, 9 feet tall, the curve would be getting very close to the axis here. Also, people that are very short, people that are 4 foot, 3 foot, less than 3 feet tall, that's very low probability, but they're there. It's just smaller probability. So before we get into 6.1 and the details of the normal distribution, I want to say this a little bit more carefully. If a continuous random variable capital X, so that's like the proper noun version, is distributed normally, or has a normal distribution. We write X is distributed normally, capital N, with a mean of mu and a standard deviation of sigma. And those are the standard symbols there. That's the mean of the whole population. That's the standard deviation of the whole population. These are the two parameters of the distribution. But this, saying that it's normal, is the main thing here. Normally distributed. That's the compact notation for it. And if I write this, I'm actually going to put a y-axis for this picture and have my normal distribution. To draw this, I like to start by drawing my axis. That's the x-axis, where x is what an individual's measurement is. If the mean is here, then that's the top of the curve, the top of the bell. And I want to do the left side first, and then the right side, so that I can kind of see the left as I'm drawing the right and make it symmetrical enough that it's useful. The area under the curve is equal to 1, the total area, because it's a probability distribution. We'll get into a little bit more about what the standard deviation means in terms of this also, but I do want to show you the functional definition in terms of the function that describes the curve. And we're not going to use this, but it is a function, an f of x. And its equation is complicated. It's 1 over sigma square root of 2 pi e to the negative 1/2 x minus mu over sigma squared. So the f of x, the x variable, I would plug in that x value right there. That's the only x in the whole expression. And then given these parameters mu and sigma, sigma is here twice, but it's the same value. This is another constant that shows up in this formula. We don't have to use this. We're going to use our calculator functions to find these values. So that brings us to 6.1. Which is called the standard normal distribution. And I've got a little bit of an abbreviation for this phrase. So the standard normal distribution, same thing, is a normal distribution, of course, of z-scores. So the z-scores that we've calculated before, the standard normal distribution is not a distribution of x values or data values, but of the z-scores of those data values. So it's going to have the same shape. It's going to be a normal shape of the curve, but it has a couple special properties. First, a z-score can be defined as the following: the number of standard deviations to the right of mu. Let's say for a given x value. So a particular value of the variable x, the z-score for that value is how many standard deviations it is to the right of the mean. It could be to the left of the mean. That's just going to mean it's going to have a negative z-score. But we've seen the formula a little bit before. I have an example to kind of just demonstrate what this z-score means for a data value. And so here's the example for a normal distribution with mu equals 5 and sigma equals 2. The value x equals 11, so an x value is 3 standard deviations above the mean. The mean, of course, is 5 mu. Standard deviation. A standard deviation is 2. The standard deviation is 2. 3 of those, 3 2s, that's 6. And what it's saying is that 11 is 6 above 5, 6 more than 5. To see it as an equation, x is equal to mu plus z times sigma. That's the x value is a certain number, the z-score number of standard deviations above the mean. So we add that to the mean and we get the. So in this case, what this means is my value of 11 is equal to the mean is 5 plus 3 times 2. The z-score. Oh, let me write that as my conclusion. The z-score of x equals 11 is z equals 3. Or just, I mean, we didn't have to find it. It says it right there. But if we were looking for the z-score, it's 3. If we were looking for the data value that corresponds to the z-score of 3, we could fill in this, like I did here, and we would get the number 11. So it works both ways. There's a different formula that we'll see, but this is it. The other formula is just rearranged version of this. All right. This is kind of going to be a little bit of an example, but it's more about the formula and the connection between the standard normal distribution and just a normal distribution. So the standard one is very specific. If x is distributed normally with a mean of mu and a standard deviation of sigma, and if I had those numbers, I would know exactly what the distribution is. I know it's normal. I know it's got these two parameters. That's it. But if we have that situation, then z, and I'm going to try and make it a capital Z here, just like we do a capital X for the proper noun version of the variable, capital Z for the distribution of z-scores, the little z's. That is distributed normally with a mean of 0 and a standard deviation of 1. So it's a very specific normal distribution. It's normal. The mean is 0 right in the middle of the number line, and the standard deviation is 1. It's just part of the standardizing to have that equal to 1. And that's where the z-score is equal to x minus mu divided by sigma. So that's kind of the connection of just a normally distributed variable to the standard normal distribution of z-scores. And this is how you can get a z-score for a variable. Provided you have the mean and standard deviation, you plug the variable value, the x value, subtract the mean, divide by the standard deviation, that's the z-score. So in summary of this, standard normal distribution has mu equals 0, sigma equals 1. That's kind of what I'm talking about with this notation. It's a normal distribution with mean 0 and standard deviation 1. That's what makes it the standard normal distribution. A little bit about these z-scores as they relate to the mean. In the original distribution, if an x value is less than the mean, then the z value is going to be less than 0. Another way to say this is the x value is to the left, less than to the left of the mean. That'll give me a negative z-score. If the x value is greater than the mean, then the z-score is greater than 0. Positive z values for x values to the right of the mean. And think of this on the number line. Really, the x is greater than mu means that it's to the right of it. Positive z-score. There's only one other thing that can happen. If x is equal to the mean, if the variable or the x value is exactly equal to the mean, then the z-score is 0 for that. Right in the middle of the distribution. All right, I've got a couple examples of finding z-scores and converting. Let's look at example 6.1, it says suppose the random variable x is distributed normally with a mean of 5 and a standard deviation of 6. We don't have to look into too closely to what that means, but this whole thing means that it's normal. Mu is 5, sigma is 6. Actually, let me make a note of that there because we're going to use that. First, in this problem, we're going to find the z-score of x equals 11. So that's my note there. This question asks us to find the z-score of x equals 11. And I'm going to first write down that formula. Not like that. Write down that formula. Z equals x minus mu divided by sigma. And then just plug things in. X is 11. Mu is 5. And sigma is 6. 11 minus 5 is 6. Divided by 6 is 1. So 1, in this distribution, 1 is the z-score that goes with the x value of 11. We'll also find the z-score of x equals 17. So same procedure, different x value. In this case, my z is going to be 17 minus 5 over 6, or 12 over 6, which is 2. Before we go on, I want to point out that this z-score means, the z-score of 1, means that the x value of 11 is 1 standard deviation above the mean. Or 1 standard deviation to the right of the mean, greater than. For the x value of 17, the z-score is 2. That means 17 is 2 standard deviations above the mean. 2 times 6 is 12. And if I go 12 above 5, 12 plus 5 is 17. The next example I have, there's a little bit more to 6.1 if you want to read that, but that's the idea. It's more of the same. For this next example, example 6.2, it says some doctors think a person can lose, on average, 5 pounds per month. I think the example says it's through diet and exercise rather than surgery or something, but on average 5 per month. Now that's an average month for an average person. I think we're better off thinking of it as an average person's ability to lose that much in 1 month. So, for this problem anyway, suppose weight loss has a normal distribution with standard deviation 2 pounds. So this is kind of a big part of it. And actually, we've got everything we need here. We're going to use capital X to represent the number of pounds lost by a randomly selected person in a month. So that's how we're going to use x as our variable. Just one randomly chosen person's 1 month weight loss. So what this says, those first two sentences, that continuous random variable, it's an amount of weight or mass or something, it's a continuous variable, is distributed normally, normal distribution, with a mean of 5 and a standard deviation of 2. And actually, this is all I really need at this point. Describing the distribution like this gives me everything I need to answer their questions about z-scores. So I'm going to leave that part of it and get some space here. So for part A in this question, what is the z-score for a person who lost 10 pounds in a month? So what's the z-score? Well, I have what I need here. This is my mu. This is my sigma. If I want to find z, I need the formula z equals x minus mu over sigma. That's, the x is 10, the mu is 5. And you can see that this weight loss, 10 pounds in 1 month, is above average weight loss. Divided by 2, that's 5 over 2. 2.5 is the z-score, or z equals 2.5. Is another way to say that. So the z-score for a person that lost 10 pounds is 2.5. That's 2.5 standard deviations above the average, which was 5. In fact, that's part of the answer here. I'm going to write that out for this one. X equals 10 pounds is 2.5 standard deviations above mu, above the mean. So that's if they ask you to interpret what that means, what that z number means, that's what they're talking about. Let's do that again for part B. So I think this example is supposed to represent the variability in people's physical or physiological ability to lose weight. In this one, though, the diet and exercise, what's the z-score for a person who gained 3 pounds? So whatever happened, they didn't lose weight, but we can still calculate a z-score. The z-score for this would be, well, that's an x value of what here? Remember, x represents the number of pounds lost. So if the person gained 3 pounds, that means our x value here is -3. They lost -3 pounds. It's hard to think about it like that with weight, but you can definitely think about it like that easily with money. If you earn -$200 at the doctor's office, you did not earn money. But here they're talking about negative weight loss. It does have a consistent logic to it. Z equals x minus mu over sigma is the formula. And here I'm going to put -3 minus 5 divided by 2. Filling in the mean and standard deviation with my x value. I get -8 over 2, which is -4. And that's it. Z equals -4. This person's weight loss was 4 standard deviations below the mean weight loss. So, here is an example that demonstrates, or a concept and an example that demonstrates the value of Z numbers for comparison. We can actually compare individuals that come from 2 different populations with respect to their own populations that they come from, and compare them to each other in a fair way. So Z-scores allow us to compare data that are scaled differently. So scale kind of implies that they were measured in a different way, but really we're able to use different populations, but measure them in a relative sense to compare them to each other. So here's my example of this. Suppose X and Y, so these are the capitals, the proper nouns or the meanings of the random variable, are random variables with X distributed normally with a mean of 5 and a standard deviation of 6, and Y distributed normally with a mean of 2 and a standard deviation of 1. 2 different distributions. They're both normal. That's helpful. But they both have different means, and they both have different standard deviations, different populations. You can't really compare fairly something from this population whose average is 2 to something from this population whose average is 5. There isn't a direct way to meaningfully compare them. So what I'm going to do is find X values. So consider Z values from the X and Y values. Consider X equals 17 and Y equals 4. Which one's bigger? 17 or 4? Well, clearly 17, but comparing them with respect to their own populations is different, and the way we can do that is I don't do this kind of notation really often, but I want to do a Z for the X and a Z for the Y, so I do kind of need a different Z symbol, but Z for the X one is X minus mu over sigma, which is 2, using the formula for the Z number with the X mean and the X standard deviation. And for Y, it's the Y value minus the mean of the Y divided by the standard deviation of the Y. 4 minus 2 is 2 divided by 1 is 2. They're the same. I don't mean to say that 17 and 4 are equal, but this individual is 2 standard deviations above the mean of his own population. And this individual is 2 standard deviations above the mean of her own population. So in a relative sense, they are the same when compared to the rest of their population. In fact, I want to say that to conclude this example. Both values are 2 standard deviations above their respective means. So with respect to their own populations that they come from, they're both 2 standard deviations above the mean. The next thing we're going to look at is a better way to understand the normal distribution in a practical sense. And we're going to use it in a technical sense too, but to get a better feel for it, we're going to look at what's called the empirical rule. So empirical here has really nothing to do with the empire. Empirical just means based on observation, and kind of just call it like you see it. Empirically determined is something that you get from just observing. That's how it is. And this is true. This is not just a casual observation, but it's the empirical rule for normally distributed data. There's 3 parts to it, and I'm going to write each part, and then I'm going to build the picture, and that's where it's going to start to make sense when you see the picture of all 3 parts. First of all, about 68% of the data are between -1 sigma and 1 sigma. And I know you don't have to put the 1 there if it's 1 sigma is sigma. 1 sigma is sigma, but for emphasis here, this is 1 standard deviation below the mean. This is 1 standard deviation above the mean. And we're going to see that 68% of the data is between those 2 values. About 95% of the data in the normally distributed data are between -2 sigma and 2 sigma. So 2 standard deviations below the mean and 2 standard deviations above the mean. 95% of the data are within that range for normally distributed data set. And then finally, about 99.7% of the data are between -3 sigma and 3 sigma. So 3 standard deviations below the mean, kind of way below the mean, and 3 standard deviations above the mean, kind of way above the mean. That's 99.7% of the data. That's almost everything. The outliers, that other 0.3%, are, for example, people who are 8 feet tall. Very, very few of them. That's an extreme outlier. Also, people who are 2'6". There are people that are 2'6", but they're extremely rare. They're part of that 0.3%. That's not the middle 99.7%. All right, so let's look at this in a picture, and I think the picture really makes it more organized. For this one, I'm going to draw kind of a large-ish normal curve. Up here, it curves down. It curves back up so it doesn't go into the axis or something, but it should be symmetrical. Mine is not really that great. I can show you better than that. Something like that. Yeah, that's pretty good. So right in the middle, that's where the mean is. It's also the mode because it's the highest point. It's even the median. They're all the same in a symmetric distribution. But if I go out to one standard deviation to the right and one standard deviation to the left, equal distance in both directions. Now that's not sigma there. That's mu plus sigma. That's mu plus sigma. Now here is mu minus sigma. And this middle section comprises 68% of the area. 0.68 is what we're going to 0.68 is what we're going to call it for a probability, but 68%, that's the same number. Now if I go 2 standard deviations to the right of the mean, that's mu plus 1 sigma, mu plus 2 sigma, and also mu minus 2 sigma, go 2 standard deviations to the left. Between here and here, this whole middle section, that's the middle 95%. So I'm not going to shade this. The book, I think, uses some shading to make this a little bit more readable. But the idea is, if we go out 2 standard deviations, 2 z number, or 2 z's in each direction. By the way, this would be my x-axis. We could call it a z-axis if it's just z numbers. But here, if I go 2 standard deviations, in between those two, 95% of the data. And if I go another, so out to mu plus 3 sigma, and out this way to mu minus 3 sigma, from here all the way to here, that is 99.7% of the data. So this is a property of normal distributions that we can use to just be familiar with what does it look like. Well, that looks like most of it right there. 68 is more than 2/3, 68%. So more than 2/3 of it is in this middle section. 19/20ths, or 95%, is between here and here. That's almost everything, kind of, other than the little 5% that's left. But then 99.7% is between those two far. And there's still, you can see, I think this should probably go a little bit smaller here, but you can see there's still some area over here and still some area over here. That's the other 0.3%, the extreme outliers. So for this reason, the empirical rule is sometimes called the 68, 95, 99.7 rule. And that's an awkward name, but if you can remember this name, it's got the numbers in it. So I think it's also a very good name. If you look this up on Wikipedia, they've got an explanation of this, and I think they just call it this, 68, 95, 99.7 rule.